Right, in this video, we're going to look at the radioactive decay equations, and we're going to go and jump straight into it. So before we observed two new quantities called the activity and the number of nuclei. Now, we obviously defined activity as being the becquerel, one becquerel being 1 disintegration per second, and the number of nuclei just being the number of nuclei. So there's no real unit associated with that. So there is a link between these two values, and it's an equation that looks like this. A is equal to lambda n. Now, this is not the wavelength, okay? A lot of people will look at this and go, oh, lambda, I know what that is. That's the wavelength. Unfortunately, that is not the case. Lambda, in this case, is what we call the decay constant. And that decay constant is a really important constant because effectively it is the probability or likelihood that a nuclear radioactive particle will decay. So it's the probability or likelihood that a nucleus will decay. Now that is interesting because we obviously suggested that in the previous video that radioactive decay was spontaneous and random. Well, again, yes, it is spontaneous and random, but we can still kind of suggest what the probability of nuclear material that a particle will decay per second, which interestingly throws up what this unit is. So if this is a number of decays per second, so a number of decays or disintegrations per second, and this is the number of nuclei, i.e. the nuclei that will decay or that could decay, then this must be the bit that is the per second bit because the decays and the nuclei is linked, but the per second isn't. And so as a result, the lambda has the decay constant has a unit of seconds to the -1 because effectively it's telling you this is the amount of nuclei that can decay per second. So the number of nuclei that can decay per second here. So this is per second. So when we have a number of nuclei decaying, we have the decay constant that gives us a activity there that is in becquerels. Obviously, you can work this backwards and rearrange it as you see fit. So that is lambda. Now, there are other equations that you need to know about, and because, as we saw in the previous video, the radioactive decay is an exponential decay. This exponential decay, like that, so n and t. So we have that exponential decay. Now, as you would expect from an exponential decay, you have an exponential equation to go with it. And that exponential equation looks like this, where the number of nuclei that you end up with after a certain amount of time is equal to the number of nuclei you start with, n0 times 0, you can think of it like that, e to the power of negative lambda t. Negative because it's a negative exponential, and the time, t, is the time that has elapsed to get from this to this. So it might be interesting just to put that in there. That's the time there. So the time taken from get to n0 to n is that time right there. And so we can utilize this equation and rearrange it. And we'll probably do that in lesson as required. The third and final equation, I think, is the most important equation. It's one that's used very often, which is the determining the decay constant equation. Now, obviously, you can determine the decay constant from this equation, and you could determine it from this one if you really wanted. But the most easy way to determine it is like this. Lambda is equal to ln, right, ln2 over t half. Now this is a really, really important equation because it means that in any exam question, they can give you one piece of information and expect you to work out lots of other things. So they can give you the half-life. ln2 is a constant, and the lambda, the decay constant, is found by doing ln2 over the half-life. And so if we know the half-life, we can work out lambda. One thing I will say about this equation, there are variations on it, and as we said before, A is directly proportional to N, so we can actually say that A is also equal to A naught e to the power of negative lambda t, because you can also have A up there as an alternative to your y-axis. And so you can use either or equation, and the time is the same and the proportions are the same, and those values are linked only by the decay constant. So an important little observation to make there, really, more than anything else. Be wary of using what you're going to use the time in. Please be aware that if you're going to have a very, very active radioactive particle, that the time really should be in seconds. Whereas if you've got a very slow acting one, I don't know, something with a half-life of thousands of years, then you can actually leave this in years, because the actual final values that you get out here will be so rounded that you won't notice the difference between a year and between the conversion from a years to seconds. So just watch out for that. I mean, if in doubt, always go in seconds, but bear in mind, for very large times, you can get away with using years.